Okay, so more derivations of circuits from chapter 2, and as I said a moment ago in class, you are applying either KCL or KVL to the circuit and Ohm's law over and over again. The trick is just recognizing what's going on in the circuit. And then also being consistent in labeling plus and minus signs and obeying what you labeled into the circuit. So more examples. So first one's kind of a simpler example, but it's an important concept because a circuit like this is called a voltage divider. Voltage dividers are used in all kinds of much bigger circuits. So a much bigger circuit might be powered with 12 volts, but somewhere inside the circuit you need 5 volts. So you have to divide the voltage down, and it's done with a circuit like the one that you see on top here. So voltage dividers, how they work. Oh, my pen changed colors back again. Let me get a better color. I don't like using the red. Okay, so I'm just going to analyze this circuit. It is a loop circuit, so loops are Kirchhoff's voltage law, right? We like to use loops. Would you like me to analyze it with a clockwise loop or a counterclockwise loop? Do you care? You always do counterclockwise? I always do clockwise because that's the way I went to school. That's called the conventional current flow way, versus the other way is the actual electron flow way. This is a DC circuit, so I'll make a capital I. So that's conventional circuit flow. So in conventional, this is a minus sign first for KVL. So this is a voltage rise, and then all the resistors are voltage drops. So they will have, this one's already assigned, but I would put plus minus because I have voltage rises equal voltage drops in the circuit. So that's, and also power supplied will equal power dissipated in the circuit. Each resistor dissipates power. So I'm going to write KVL for this circuit. So I have minus V plus I R1 plus I R2 equals 0. So that's KVL, and I just look at what sign I hit first. So the voltage supply, I hit a minus sign. The resistors, I hit the plus sign first. So that's how I made my sign conventions on there. So then I get V equals I R1 plus R2. And then I get I equals V R1 plus R2. So now I know what the current is in the loop. There's one current in the loop, one and only current, no other currents in there. And now I can compute the voltage across each resistor. So I'll say that voltage 1 for the voltage across resistor 1 equals I R1. Only one I in the circuit, so that's V R1 plus R2 times R1, or V, that's your source V, right? V source always. Sometimes I like to make that distinction just to make sure I'm clear. R1 over R1 plus R2. Similarly, we can find the voltage across resistor 2, which I call V2, which is I. And look, I was inconsistent. I switched back to my little I's. Sorry about that. I R2, which you will, if I do the algebra, it will be R2 over R1 plus R2. So, so what you find out is that the voltage across each resistor is a ratio, the resistor divided by the total resistance, series resistance in the circuit. So I'm going to do a numerical example to show why that's a voltage divider. So note that these calculations are voltage across the resistor. It's not necessarily voltage at that node or that node or that node. It is the voltage that is across the resistor. So, so numerical example, for fun of it, I'm going to make this 10 volts. I will make the R1 be real numbers. R1 equals 2.2 k ohms. R2 equals 6.8 k ohms. So your book likes to use unreal values of 2, 4, 10, you know, weird resistant values that are very small. I'm using more realistic values using the kilo ohms. And all.
So if it says that V1 is equal to like 5 volts, that's not saying it's 5 volt at either to the left or to the right of the resistor.
It is not.
Difference between.
It is saying it's the difference between the voltage here at A and the voltage here. I'll make that B just sort of sum it for the fun of it. So V1 is VA minus VB, or the voltage across this resistor. That's why I was going to do a numerical example, because it kind of makes it hit home here. So if I use my voltage divider rules here, I found out that V1 was 10, R1 was 2.2 K, and 6.8 K plus 2.2 K. Right? In reality, the K's all cancel out. All the K's can cancel out there, and you'll find out that the voltage across R1 will be 2.44 volts. I do the same thing for V2. V2 will be V source times this ratio, so it's going to be 6.8K, 6.8K plus 2.2K. And then you'll find out that this is 7.56 volts. So as a check, what's 2.44 plus 7.56? 10. Yes, KVL is obeyed, right? So you can say I drop 2.44 volts across this resistor, and I drop another 7.56 volts across this resistor. But if I look at the node voltage, maybe I have my voltmeter with the black probe here and the red probe there. I'm measuring voltage. I would measure right here 10 volts relative to my 0 reference point. And then I would go across the resistor and I would drop 2.44 volts. So then at that node, voltage at B would be 10 minus 2.44, which would equal 7.56 volts, right? So if I measured between here and here, I'd see 7.56 volts. Between here and here, I see 10 volts. Between here and here, I see 2.44 volts. So voltage across this resistor is 7.56. So I start at 10, I drop by 2.44 down to 7.56. I drop 7.56, I'm back down to 0 volts.
So that chassis ground you could have put right after R2.
I can call my reference point any place I want. I'm measuring relative to here. Yeah. So this is 10 volts higher than here. This is 7 volts higher than here. But this, if I use this as my reference point, let's say I put my black probe here and measure between here and here, this point will be 2.44 volts higher than this point. Okay? So voltage dividers are actually very common. You want to divide down some source voltage to smaller voltages that you need in your circuit, and so you just use a voltage divider network.
So did you see that there's 0 volts all the way from R2 to back to the...
Well, the voltage here, the potential that's here is the same. It's constant. It didn't change if you assume ideal conducting wires with no resistance whatsoever. This voltage is constant here. So if this is tied to ground, then all of this along here is at 0 volts. I think I can pause here for a second. I have to answer a question. Oh, yeah. Can I get back with you in a moment? Yeah. Okay. Sorry for. Yeah. I don't even want to do it. Keep. Fine. Continue recording. Okay. I'm still recording, right? I think I am. I don't get any indication. Okay, sorry, I'm messing with my tools here that are new for me this semester. So let's continue on. Okay, so any more questions about voltage divider? Okay, so you actually get to the point where you can just do this by inspection. The voltage at that node, voltage at that node, when you have a series circuit like this. So a parallel circuit ends up being a current divider. So if I look at my parallel circuit, I have a total current here, and it's going to divide between these two legs of the circuit and recombine back here. So there's my pin switch color again. So this is I can call it I total if I want. And what's the current in this leg down here? This is one branch, right? By virtue of being one branch, that's also I total. So I total goes into the circuit. Part of the current goes this way, part of the current goes this way, and this is conventional current flow. And then they recombine back here, and you have conservation of charge occurring in this total circuit, correct? So we start with KCL on this circuit because it's a parallel circuit, and so your instructor intuitively told you that you need KCL on this circuit. I'm just thinking the best way to present this for a moment. Can we find what the total resistance is of this circuit? Can we find what I total is? We can by, if you go back to when we talked about last time using parallel circuits and making an R equivalent. This is still I total, because I total goes into some equivalent resistance right here, right? So our equivalent is R1, R2 over R1 plus R2, which came from 1 over R equivalent is 1 over R1 plus 1 over R2. That was, we re-derived that last time. That was for parallel circuits. So we can find out what I total is from this relationship. I total equals V over R equivalent, or V equals I total R equivalent. So we know that relationship about the circuit right now. So V is right here all along this node. Completely, I'm going to call this my reference point. This is 0 volts. V is everywhere along here, correct? And 0 is everywhere along here, along this node. There are two nodes in the circuit. So that means the voltage across here is the same as the voltage across R1, is the same as the voltage across R2. Same voltage everywhere. So therefore, I1, using Ohm's law, is V over R1, and I2 is V over R2. So I can substitute what V is into these two relationships. I know what V is. And when I get that, I get I1 equals I total R equivalent over R1. Likewise, I2 is I total R equivalent over R2. So simplify that down, make the substitution for what R equivalent is. This was R equivalent, and you'll get I1 equals I total R1, R2 over R1 plus R2. That was R equivalent, right? And it was divided by R1. So that was R equivalent right there. And right, okay, so and then you do that math and you get I total R2 over R1 plus R2. So that's I1, and in a similar fashion, I2 will be I total R1 over R1 plus R2. So this is the current dividing. It's saying I total is here. A fraction of the current goes this way. A fraction of the current goes in the other leg. So the fraction of the current that goes into I1 is this ratio right here. The fraction of the current that goes into I2 is this ratio over here. Notice the numerators are the other resistor in the circuit. This consequence of that is that larger current flows in smaller resistor, right? Which is Ohm's law. So, and if you add these two back up together, you come back with the total current. I1 plus I2, add these two together, and you'll come back. You'll get R1 plus R2 over R1 plus R2, and so you'll get I total. So that's the current divider. Divides the current into two legs. Now comes the hard part. The delta to Y connections or Y to delta connections. So this looks like a delta, upside down delta, because delta symbol is this, right? So that's an upside down delta. You should be convinced easily that if I just slide this out this way, slide this wire out this way, that that's the same circuit down below, correct? Yeah, so this one's called a delta circuit, but this one's called a pi circuit. So sometimes when people talk about delta to Y's, they'll say it's a pi to something. And that's because this is the Y circuit, Y after the name person here. Here's a Y circuit, but if I just bend the leads differently, it becomes a T circuit. So these circuits are not, our configurations like this are often inside another circuit, and you cannot clearly see that they are a series or a parallel circuit. And that's why we sometimes need to convert between a delta to a Y or a Y to a delta, and I have a nice example to do at the end here. So let's do the conversion from a pi to a Y, or delta to Y, or a pi to T circuit. So I have it drawn as a pi right now, but that's really a delta, right? Your textbook mentions doing things with a 3-port circuit, and then they do the example and make it a 4-port circuit, but the 4-port circuit is really a 3-port circuit. So this is a port 1, port 3, and port 2 and 4 are really the same, correct? And when I draw circuits like this, I usually put a test point right there. So port 1, 3, 2, and 4 are the same. Now if I take a multimeter and I connect it between ports 1 and 2 with this circuit just like that, what resistance would I measure? So resistance between 1 and 2, that's what's going to be between terminals 1 and 2, is I see that these are in series. These are nothing. These are just like hanging out wires in the air right now. They're reference points. They're not anything. So if I were to see the resistance between there, I see these two guys are in series, and these series are in parallel with that guy. So it would be RC plus RA in parallel with RB. So if I put my multimeter between here and here, that's the resistance I would see. Remember, these are nothing. These are just reference points. Okay? So that's for my delta circuit. But I want to convert my delta or pi circuit to a Y circuit. So I want to convert it to something that looks like this. 1, 3, 2, and 4. So I'll call this R1, R2, R3. So let's just say I can't, this is embedded somewhere and I can't use it, so I want to convert it into something like that, and I have a good example to do of that coming up. So now I look at this circuit here, and I put, so this is the pi, sorry I call it delta, and this is the y, also called the T circuit. So if I put my multimeter between here and here, what do I measure? What would I measure?
Between 1 and 2?
Yep. So this is a resistor sticking out in the air as far as I'm concerned. It's just hanging, sticking up out of my proto board, this resistor right here. So it doesn't affect the circuit at all. If I measure my resistance between here and here, I will see R1 plus R3. This is not affecting my circuit at all, because there's no loop here. It doesn't complete any circuit. Even if you use your multimeter, you have to complete a circuit. So if I have my ohm meter in here trying to complete the circuit, I have a complete circuit to measure ohms. Okay, so that's what I measure. So I have this circuit, I want to get this circuit. I have an expression for R1, 2, R between 1 and 2 here. I have an expression for R between 1 and 2 here. So what I'm going to do is set R1, 2, that's the delta, equal to R1, 2, that's the Y circuit. And then I will get that R1 plus, well, let's do it in the order that I wrote it. RC plus RA in parallel with RB equals R1 plus R2. This plus this in parallel with this, I'm going to use the fact that if I have two resistors in parallel with each other, R, give me the X parallel with RY equals RX, RY, RX plus RY. That's the parallel relationship. So I can go ahead and do that. RA plus RC, put it in order, times RB, RA plus RC plus RB equals R1 plus R2. Okay, so the thing that we have going here is that we know RA, RB, and RC. These things have known values. We are trying to calculate R1, R2, R3. So these are three unknowns, and so I have to write three equations and three unknowns in order to be able to solve. Right? Three equations and three unknowns, and then I can solve for the three unknowns. So I have a first equation right here. R1 and R2 are unknowns. These are all known values. So this is I can go now and look at the other terminals, which are a little bit confusing to look at. So I actually flipped circuits around and looked at them. But when you do that, see, I think I did it on the back of my sheet because they were kind of confusing to look at. So similarly, R between 1 and 3. So between 1 and 3, so you have to think about that you're flipping the circuit around. And what does the multimeter see if I connect it between 1 and 3? Same thing here. So if you flip the multimeter around, or flip the circuit around and draw it again, you'll get R13 equals R13 of the pi network equals RC in parallel with RA plus RB, and R13 of the other one, pi, so I'll say T, equals R1. Oh, I wrote it wrong. I wrote a mistake. So let's look at what it is. Of the T network, I want to look at between R1 and 3. Should be R1 plus R2. Which one where did I make the mistake? I should have something different here. This one. This is where I made the mistake. Nobody caught me. R1, 2. If I measure, it's R1 plus R3, right? And then the last one you get is R3, 4, between 3, 4, because this one doesn't count. It's just one node. R3, 4, you'll do the same thing, will equal R2 plus R3, which will also equal, oh, I took shortcuts, RA, RB plus RC. Okay, you do some ugly equating these two together, you get 3 expressions and 3 unknowns, and then you have to do some substitutions and solve for R1, R2, and R3. And we do that, you get R1 equals RB, RC over RA plus RB plus RC. And you'll get R2 equals, and it's always going to be the resistor's not used in the numerator. So RA, RC, RA plus RB plus RC. I thought about giving this as a homework problem. Derive this for yourself. RA, RB, RA plus RAB plus RC. So after some math, after you do some math in here and you get 3 equations and 3 unknowns and you do a bunch of substitutions, you end up being able to solve for R1, R2, and R3. So basically what I'm doing is converting this circuit into this circuit. So an easy thing that people like to do to remember it is draw the circuit that they're converting it into in the middle, like so. So this circuit that was original on the outside becomes this circuit that's in the middle.